Welcome back to Lesson 5 quiz, and we left off at number 6. Let's go ahead and erase a little bit. But number 6 states, select the correct statement in regard to reinforcing concrete columns. And A says that the tied columns generally have a circular cross section, and that's incorrect because you can have a tied column that looks like so. I hope that makes sense. So that's your tie, and that's your reinforcing, longitudinal reinforcing, meaning going, when I say longitudinal, I mean going the length, and the length of the column would be this way. Oops. So here's your column. This would be your longitudinal reinforcing, and then you'd have your ties like so. So they can be circular or square or rectangle. They could be whatever you want, really. That's what you'll see most often. Alright, so that's A is incorrect. B, spiral columns can support more load than tied columns if all load factors are same. And that is true, and you'll look at the factors. Let's go to page 97, and it should have, actually go to page 98. And you can see the strength reduction factor, phi, once again, if my Greek is correct, is equal to 0.75 for spiral and then 0.7 for tied. So as you can see, the strength reduction factor is less. So you're multiplying, you get 75% if you're using spirals and only 70% of capacity if you're using ties. So ties are not as strong, you could say. You are reducing your strength more with ties as opposed to columns. So I would say that B is correct. Because of their, well, it's a possible correct. I'm assuming it's correct. Okay, go to C. Because of their stockiness, reinforced concrete columns are not generally subject to bending moment, and that's horribly incorrect. For instance, let's say you have a bridge pier, and it's what we would call a double. That's a horrible drawing. But this is a cap. So here's your ground, and let's say it's long. You'll have a rock socket or whatnot. Obviously, this isn't the most perfect drawing. And then you'll have your beams on top here. But this column, these columns, the longer they get, a lot of times you'll have big issues with these columns, and bending is your major. You're not going to have any issues axially. The big issue is going to be your bending, especially if you have long spans, let's say 125 foot or 120 foot pre-stressed concrete span. You go in, here's from looking this way, and here's your other bent. And the temperature loads, if you get to a point where this is going to be an integral, where you end up pointing to diaphragm and the slab here, the temperature loads from these longer slabs, and sometimes you'll get like 3 or 4 units where this is integral slab. When I say 3 or 4 units, I meant 3 or 4 spans per unit. So you have to find the center of movement, and let's say the center of movement's right here, and these will move, maybe a few inches at the top. It'll force it over. It's gonna move because that's just what happens when the concrete wants to expand. It's going to expand, and since this is so long, it's actually pretty flimsy. So if you have a short column, let's say there's a ground right here, and then all of a sudden it comes down to a longer column over here. This column is obviously not going to move as much. It's more stiff than this column, but it's still bending is a huge factor, is what I was trying to say, and that was probably not needed. Went a little far on that explanation. So C is incorrect. It says because of their stockiness, reinforced columns do not have to worry about bending. That is incorrect. You do have to worry about bending. That's probably the major part of it in some cases. If they are nice, short, stocky ones, then yes, bending won't be an issue. In reinforced concrete columns, the longitudinal reinforcing bars carry all the vertical load, while the concrete serves to protect and confine the bars. And that's incorrect. I'm going to say the vertical load, actually I would assume that most of the concrete is going to be able to handle that. But they do work together. And mostly I would say that the longitudinal bars, reinforcing, are to protect against, or to provide capacity for bending. Alright, so B is your answer for number 6. Number 7, what is the ultimate moment capacity? And once again, I would call it moment capacity. I would say phi mn at this point. Mu, I would say, is load. But there's, you kind of have to figure out what they're asking. I would say it's phi mn. And it says a reinforced concrete beam with B equals 20 inches, D equals 46 inches. Let's write these out. B equals 20 inches. D equals 46 inches. 4 number 8, so that's area steel equals 4 times the area steel of a number 8. Let me go to page, and I probably should figure out what they're going to give you for resources. I need to look that up before I get into this any further. And then they have 4 number 8s. And number 8 has a 0.79, page 87, 0.79 inches squared. And that equals 4 times 0.79 equals 3.16 is your area steel. What else do we have? F prime C equals 4 KSI. Fy equals 60. And that's typical. Assume that A equals 9.2. Remember, we could figure out A, but we don't need to. Actually, let's do a quick, what is A? A equals, and I don't even think you guys went over this in the study guide. But this is the equation. And we have all the stuff, so you might as well just take a step and see what it actually is. It may be actually 9.2 exactly. I bet you that's what they did. 60 KSI over 0.85. F prime C is 4 KSI. And B is 20 inches. And that equals actual A equals 8.5, 0.85 divided by 4 divided by 20. Doing a bad job of saying what I'm doing. I got 2.79 inches. Is that right? What am I doing incorrectly here? Let's look again. You have a D of 46 inches. That's an awful high A. But whatever they got is what they got. We said maybe our A area steel was wrong. 4 number 8. We said 4 number 8 is 0.7. That's right. Alright, well, it is what it is. 3.16 times 60 divided by 0.85 divided by 4 divided by 20. Again, units look right. 2.79. Alright, well, forget this. They said say 9 equals 9.2. That's what we're going to do. So I may have messed up on this, and hopefully you can go back and figure out where I messed up. But my actual A is way different than what they got. But anyways, phi mn equals phi AS Fy D minus A over 2. Remember, you divided by 12 because we're going to go in here with we want foot kips. So let's go down here. 0.9 AS equals 3.16 inches squared. 60 KSI. D is 46 inches minus 9.2 inches divided by 2, and we'll take that all divided by 12. And we get, remember this is changing it into feet, foot kips. Right now we have inch kips. 0.9 times 3.16 times 60 times, open parentheses, 46 minus 9.2 divided by 2, close parentheses divided by 12 equals 588.7 foot kips. And that is answer number A, 588.7 foot kips. And once again, I'm starting to get worried why I messed that up. But anyways, they gave us what they gave us, and I'm not going to worry about it. So your answer is A. 588 foot kips is your capacity. All right. Moving right along to number 8. Which reinforcing steel arrangement is correct for the two-span reinforced concrete beam shown below when supporting a uniformly distributed load across both spans? So you have a beam, and it's looks like so, and it says a uniform live load. So on a uniform live load, let's kind of throw out there a shear and moment diagram. What would it look like? You're going to let me think. You're going to go up a little. And you're going to go down. Sorry, I have to think about this. And then you go, yeah, probably right there. Then you go up, and then you go down, and then you go up the rest. Which, on second thought, it should be like this. I'm guessing you're... Wait, does that make sense? No. Sorry. I'm doing a bad job of explaining this. Goes up a little, comes down more. It should look like that. And then if you think of your moment diagram, it's gonna look, it's starting to go up. It goes to 0. I hope that makes sense. Where this is negative moment, this is positive moment. So you're gonna have in other words, I hope I did this to try to make this make sense. Here's your deflection. And you can actually, you'll find out later that you can, this is part of it, is your deflection is going to kind of look like this. It's going to want to do this, and it's going to go up like that. That's what's wanted to do. So you can see its negative moment is going to want to push it up. Alright, so the question is, where do you want your steel? And if it's me, I want the steel. When you have positive moment, I want the steel on the bottom. So here's what we want. And the negative moment, I want the steel on the top. So something that looks similar to this. So let's look at what looks similar to this. And if I'm making this, I would rule out D, because D only has it on the bottom. I would even go as far as to rule out B and C. Or maybe not C, but definitely B, because B right here is where you're going to have your maximum moment. You don't want to take it out there. Then I come to A and C, and I'm kind of split over those. I don't know which one I would want. It kind of depends on your dimensions, but A looks all right because it's right here and then it goes up, right here and it goes up. So I would say A would be all right. And then you look at C, and it's got here, and it also has down here, and these are overlapped. So I think either would be okay. And it looks like, let's go see what they said. They said C. In reality, I don't know if I like that answer at all. But take it with a grain of salt. What would you do? Ask some engineers that you know. Here's what I would do, and have done in the past. Voila, done. You put negative steel on top, you put positive steel on bottom, and you design it for each. And usually just run it the whole way because it's easier that way. Alright. And I'm going to go ahead and stop right here. We have 2 more, and I'll see you for part 4 of the Lesson 5 quiz.